Hello students, welcome to my lecture. In this video, I will discuss a few important concepts from current electricity chapter. These important points will help you solve the problems. Okay, let us start. So in the current electricity chapter, the first point I want to discuss itself is the first current. Simple, the current we define as average current is simply amount of charge crossing across a cross section for a given time interval. Instantaneous current is simply defined as the rate at which charge is flowing, dq by dt. Okay, so from here I can write as the amount of charge q that is crossing will be is integration of I dt from the time interval t1 to t2. So these three formulas or definitions are important to understand the current. That is, average current is the amount of charge that is crossing at a given cross section. For instantaneous, it is the rate of flow. Okay. Then I want to define the current density. Current density that is J. It is a vector quantity. So it is defined as current I at any cross section is J dot ds. ds is the cross sectional area. Okay. So J is formally we can define as the J is simply current per unit area. Current per unit area. Okay. So important relations related to this current density will be, so J is equal to minus NeVd. N is the number of electrons, that is charge carriers, number of electrons per unit volume, number density. Of course, E is the electric charge, Vd will be the drift velocity. So drift velocity is defined simply as, so it is the drift velocity. Drift velocity or simply drift speed. Okay. So the drift velocity expression will be E tau divided by m into electric field. In vector notation, it is opposite sign. So from these two relations, what can I write? J is equal to minus Ne drift velocity minus E tau divided by m into E. That is J is equal to N E square tau by m into E. That is sigma into E. So here E is the electric charge and T is the relaxation, average relaxation time. So relaxation time means time gap between collision to collision. M is the mass of electron and sigma is the conductivity of material. Sigma is the conductivity of the material. So rho is equal to 1 by sigma, that is resistivity of material. Resistivity of material. Suppose if I take a simple conductor, say a linear conductor generally I'll take. Let us connect it to a battery which has a potential difference of delta V. Let's say the length of the conductor, that is from positive charge to negative charge, from high potential to low potential, along which the current goes, it is the length, and this is the cross section along which the electrons are crossing is A. Then here I can write J is equal to sigma, that is 1 by rho into E. J means here current per unit area into 1 by rho. Electric field can be written as potential difference divided by length. So from here delta V divided by I is equal to rho L by A, which is a constant for a given conductor. Constant for a given conductor. Constant for a given conductor. I call this quantity as the resistance of that conductor. I call that is delta V by I is the rho L divided by A, that is resistance of that conductor. Resistance of this conductor. So it depends upon the length and area of cross section along with the material with which it is made. Okay. So generally there are some type of questions based on this resistance is equal to rho L by A. So something like they'll ask, there is a wire, so I'll stretch it. So when I stretch this wire, what will happen here? Length will increase and radius will decrease. But one thing will be constant, that is volume is constant. Volume V is equal to A into L will be is equal to constant. So when I stretch, during the stretching process, volume will be constant. So that resistance can be written as then rho L square by area into volume. So even you can write, if I multiply with area, rho into volume divided by area square. So area can be written as pi r square for a given conductor. So pi r square will be the area. Okay. So generally in the competitive exams, there is questions based on this resistance. Okay. So now variation of resistance with temperature. Variation of resistivity, I call resistivity with temperature. With temperature for a conductors. For a conductor. So for a conductor with increase in temperature, there is a decrease in the resistivity. Resistivity will decrease. So that coefficient, temperature coefficient of resistivity is defined as fractional change in the resistivity per unit rise in the temperature. So from here I can write, so rho is equal to rho naught into 1 plus alpha T is the temperature, or otherwise I can write rho 2 is equal to rho 1 into 1 plus alpha into T2 minus T1. So sometimes if I ignore the change in length and area with rise in temperature, resistance R2 also can be written as R1 into 1 plus alpha into T2 minus T1. So alpha is the temperature coefficient of electrical resistance, that is R is equal to R naught. If in the initial temperature is 0 Kelvin, then I can write something like this. So for conductors with increase in temperature, resistivity will increase. If you want to plot a graph of resistivity versus temperature, resistivity versus temperature, the graph looks almost like this. Okay. So for high temperatures, it is resistivity is directly proportional to temperature. For low temperature, it is resistivity is directly proportional to T cube. So remember that even at 0 Kelvin also, there is some resistance is present, resistivity is present. This is the impurity resistances. Okay, it never comes to 0 for a metal or conductor. If I talk about the another element, important thing I need to discuss, it will be superconductor. For a superconductor, the things are different. So with decrease in temperature, resistivity decreases abruptly at a certain temperature known as the critical temperature. Resistivity will become 0. This type of materials are known as the superconductors. Okay. Remember, semiconductor is something different. So semiconductor is something different. So which is something like with increase in temperature, resistivity also increases. But for a conductor or metal with increase in temperature, resistivity decreases. Okay. I hope it is clear. Okay. So another point I want to discuss here, power. So electrical power is simply defined as the product of potential difference multiplied by the current. So by using the Ohm's law, by using the Ohm's law. This is what the Ohm's law here. Delta V by R constant. That is V is equal to IR. I can write it as I square R or otherwise V square divided by R. So this is also important to solve the problems. How much amount of heat is liberated? Amount of heat liberated is integration of P into dt. So that is I square R into T is the time in seconds or depending upon the question. So how much time the current is passing through a given conductor. So this is the power. After that, so let us discuss about cell. So a cell generally consists something like, symbolically will represent something like this. There will be a battery. So something, it is a potential difference will be there. There is an internal resistance. This end I call it as A and this end I call it as B. If the current is coming out of the cell, then the potential difference between the two ends VA minus VB is equal to E minus IR. This is the case of discharging cell. Discharging cell. Then what about charging cell? So when the same thing, for example, I have here AB. When the current I is going here, when the current is entering, this is the charging type. The potential difference VA minus VB now will become E plus IR. Okay. So again, there is important concept, cells connected in series and cells connected in parallel. When the cells are connected in series combination of cells, the one cell will be something like this. Another cell is something like this. These are all connected in series across a load resistance R. Let's say this is R1E1, this is R2E2, and this is R3E3. Then equivalent resistance or equivalent EMF will be E1 plus E2 plus E3 and so on. Similarly, R equivalent will be R1 plus R2 plus R3 and so on, as they are in series. Similarly, parallel combination of cells. There is a cell 1, there is a cell 2, so there is a connected to a load resistance R. So R1E1, R2E2. Then what is the E equivalent? So be careful, the formula is little bit different. E1 by R1 plus E2 by R2 and so on, divided by 1 by R1 plus 1 by R2 and so on. Reciprocal. So similarly, what is R equivalent? So 1 by R equivalent will be is equal to 1 by R1 plus 1 by R2 plus and so on. This is for the parallel combination. Okay. Another important theorem is that I want to discuss here, maximum power transfer theorem. So for example, I have a load resistance R here and the cell is connected to this. So what is the maximum power which is delivered to here? So simply if I write the power will be is equal to here I square into R to the load resistor, the load. So what is I here? In this I will be is equal to EMF divided by R plus R. That is, power to the load will be is equal to E square R by R plus R whole square. This is the power delivered. So if I plot a graph of this, power versus the load resistance, the graph actually follows like this. It has the maximum power when small r is equal to capital R. Here is the maximum. So R is equal to R, then I have the maximum power. That maximum power I can write it as, if I put R equal to R, it comes out to be 4 square E square by capital E square by 4R or E square by 4 times small r. So this trick also will help us to solve the problems. Then very important theorems, that is Kirchhoff's Kirchhoff's current law. The sum of the currents which are approaching a junction will be is equal to sum of the currents which are leaving a junction. Kirchhoff's current law. Then Kirchhoff's voltage law. So in a loop, the sum of the potential drops will be is equal to 0. So this KCL not only for currents, even for charge also, sum of the charges which are reaching to a junction is equal to sum of the charges which are leaving. Generally these ideas are used in the capacitors. So this idea you can use for capacitors, for inductors, along with the resistors. Okay. So when you are applying the sum of the potential drops, say for example if it is a resistor, the current is I going like this. When you are going from A to B, then there is a potential drop will be there. So high potential A to low potential B you are going. The potential drop will be there, that is I into R. Suppose if you are going from, this is from A to B I am going. So I call it the drop. If I go from B to A, then it is a rise will be there. There is a rise in the potential difference. So generally I take drop means negative, rise means positive. Okay. So this is the resistor. If there is a capacitor, see, capacitor will be there. Let's say here positive charge will be there and here it is negative charge will be there. Capacitance is C. Then the potential difference I write it will be Q by C. So let's say Q with the charge here. If there is an inductor, let's say there is an inductor, assume that current is either increasing or decreasing, then definitely there is EMF here. The potential difference will be is equal to minus L into the rate at which the current is changing, di by dt. Minus L into dy by dt. So while applying the KVL, for this KVL is a current law for a junction. For any junction. At any junction, sum of the currents coming is equal to sum of the currents going. So that means it is based on the conservation of charge. It is based on the conservation of charge. This for a loop. Any loop you can take for a loop. It is based on the conservation of energy. It is based on the conservation of energy. Okay. These two laws very important to solve any problems. Be careful. Then another importantly, I'll discuss here instruments. So I'll discuss here instruments. In the instruments, first I'll discuss the galvanometer. So we all know that in the galvanometer there is a north pole here and there is a south pole here. There is a conducting loop will be there that will be suspended from a torsional wire. Okay. So when the current goes here, so because of this current there is a torque in the loop. So magnetic torque is balanced with the torsional torque. Torsional torque in the suspension wire. Magnetic torque I can write, it will be mu cross B. So mu means magnetic moment. Mu cross B is a magnetic moment, is equal to torsional constant K multiplied by the angle which is turned, K theta. So I can write will be here it is mu B sin theta. They'll keep the magnetic field is always at an angle 90 degrees here. That means magnetic moment is always perpendicular to the magnetic. So magnetic moment is defined as current passing through it I, area and number of turns into B is equal to K multiplied by theta. So clearly the theta, the angle which is turning will be is equal to A N B divided by K into I. Okay. So when you see the galvanometer, you might have noticed like that the readings will be displayed on the cover. It is a 0 here, this is 1 here, this is 2 here, this is 3 here. and this side also 1 here and 2 here and 3 here, that we don't know that clockwise currents are going or anti-clockwise currents are going in this loop. Okay, there will be a needle, that needle will be rotating, it will go from here to here, something like this. This is the rotation. That rotation angle is indirectly linked with the current. Okay, so current is here. Suppose if I want the voltage, so the potential difference V I can write as I multiplied by resistance. So that means in place of I can write V by R here. So that time this is the current related. The theta which is related to potential difference comes out to be A N B. In place of I am writing V by R. So K multiplied by R. R is the resistance of the loop and V is the voltage. So R is the resistance of the loop. So I want to define one of the important things will be here, sensitivity. So sensitivity something we define as the deflection per unit current. Deflection per unit current if it is the current sensitivity. It is the current sensitivity. If it is the voltage sensitivity, deflection per unit voltage. So sensitivity of an instrument. So how much is the deflection per unit current? Okay, so important quantity, remember. Okay, now so how you will convert a galvanometer into an ammeter? Conversion of galvanometer into ammeter. Generally galvanometers are the limited currents, limited voltages they measure. They will not measure the high voltages or high currents. Say for example, this is my galvanometer. The resistance of the galvanometer is Rg and I will indicate with the symbol G. So what I do here, I will shunt a small resistance S will be here. Shunt. Now assume that large currents are entering into the circuit. When the large currents are entering, galvanometer only allows a little currents. The rest of the currents will go to this small resistance. Okay. So these entire elements are in parallel combination. I can write Ig into Rg will be is equal to shunt resistance into I minus Ig. A shunt resistance in the sense a small resistance we are connecting across the galvanometer. Okay, this is the conversion of a galvanometer into ammeter. So with the help of this I can calculate what is the amount of currents we need to measure. Say this is the currents we need to measure. For that purpose what is the shunt you need to connect, that we can calculate. Okay, so then how you will convert a galvanometer into voltmeter so that a large potential differences you can measure. So a galvanometer conversion into a voltmeter. Say for example, this is my galvanometer. What I will do here, I will connect a large resistance R here. Now I will connect this part, remember, in parallel. Galvanometer is always connected to the parallel to the main circuit. Connected in parallel with main circuit. Connected in parallel with the main circuit. So I want to measure the potential difference across these three. Let's say here it is only a little current goes, that is Ig. The potential difference between A and B will be is equal to Ig into R plus Rg. So this way I can measure the potential difference between the two ends A and B. Okay, so this is enough related to galvanometer conversion into voltmeter and ammeter. Now one of the important thing we discuss will be the Wheatstone bridge. Wheatstone bridge. So a Wheatstone bridge generally consists of 5 resistors. Maybe sometimes here galvanometer they can kept. So let us take this is R1, let us take this is R2, let us take this is R3, let us take this is R4, Let us take this is R5 or otherwise RG, resistance of the galvanometer. When the current comes from the battery, after reaching here, it will break up into two parts. I1 is the current here. Then I minus I1 will be the current here. Then this I1 after reaching here will break into two parts. Ig current in the galvanometer. I1 minus Ig will be here. Then Ig comes here, which combines with I minus I1. So I minus I1 plus Ig. So this current combines with this current. Ig will cancel. I1 also will cancel. Then again current I will be here. If you notice here, I is unknown to me. I1 is unknown to me. And Ig is also unknown to me. I require the three equations. Take any three loops. Apply KVL. And you will get the three equations. And solve them, you will get all the quantities. The interesting thing will be, so what is the condition? Something like current going through the galvanometer will be 0. When the current going through the galvanometer will be 0, this C point and this D points will be are at the same potential. Potential of C is equal to D, that is the potential difference between C and D will be is equal to, here the potential difference between C and D will be equal to 0. This is the condition generally we call as Wheatstone bridge balanced condition. Wheatstone bridge balanced condition. This can be verified very simple. During that balanced condition, R1 by R2 comes out to be R3 by R4. Okay, so be careful while solving the problems in the Wheatstone bridge. This much is enough to solve the problems. Okay, like Wheatstone bridge, there is another thing will be there, known as the meter bridge. In the meter bridge, there are two L-shaped strips will be there with some gap between them. Okay, so here one resistance will be connected, that is known to us, and here another resistance will be connected, that is unknown to us. Okay, now a battery will be connected here. So now with the help of galvanometer and with the help of a jockey, I can touch anywhere here. Let's say these are the 2 points A and B. As usual, we know that through the battery there is a current I comes. After reaching here, there are two paths will be there. So this is one path and this is one path. Let's say I1 is the current here. I minus I1 is the current here. I1 current goes here. After reaching, there are two paths will be there. There is a current through the galvanometer. Rest of the current goes here. I1 minus Ig. This Ig after reaching here combines with this. Then total current becomes I minus I1 plus Ig. So from here the current I1 minus Ig is coming. After combining, there is again current I. So exactly almost like Wheatstone bridge. These two are the A and B points. These are the A and B points. C and D point. This is C point and this is D point. And C and D point as usual. This is my C point and this is my D point. Okay. So now AD is the something resistance of AD. That is balanced condition I am writing. That is resistance, known resistance here. That is divided by resistance of the part AD. Unknown resistance Rx divided by resistance of the part dB here. So we use one trick here. Resistance is directly proportional to length. So that means resistance R will be, RAD is rho, length AD, call it as L, divided by area. That is resistance of Rx divided by rho divided by A into. So the total length AB itself is 1 meter. So 1 meter. So that means if I measure length will be in centimeters, it will become 100 centimeters. So 100 minus L, rest of the length. Rho by A cancel. R by L in centimeter is equal to Rx by 100, 100 minus L. So with the help of this relation, I can calculate the unknown resistance Rx. Okay. I hope it is clear. Next, the important thing I want to discuss here, potentiometer. Potentiometer. So potentiometer. So obviously potentiometer is also just like meter bits only, but the length of the circuit will be here unlimited. Any length we can consider. So let's say this is the length of the potentiometer, right? So there is something like we require one battery here which gives one resistor here. So this is the EPL, right? This is the RP. Generally we call it the primary circuit. This is my primary circuit. So with the help of potentiometer, two things can be done. We can estimate we can compare EMF of batteries, and we can find internal resistance of a cell. Internal resistance of a cell. Suppose here I am connecting this with a battery of EMF something, with the help of galvanometer and with the help of a jockey. Okay, fine. So let us call this will be something like E1 R1 and search for the null point. Let's say at P point I'll get the null point. This entire network generally I call it the secondary circuit. This entire network is known as the secondary circuit. Okay. So as usual, when the current passing through will be, so that means potential difference across AP is same as that potential difference across these 2 points, as no current flows here. These two are at the same potential. No current in the galvanometer is the null point. So zero deflections, we need to search for it. Okay. So potential difference across AP is equal to, that is E1. Similarly, now you connect another battery of EMF V2 and resistance R2. Let us call the first one is VP1 and second one I call as VP2, that is equal to E2. So one thing is important here. If I want the potential difference between 2 points, I need to calculate current multiplied by resistance between those 2 points. So here A and P and here A and P. So we all know that key resistance will be resistivity rho, length, that length divided by area. So what can I write here? Resistivity between the potential difference between 2 points is directly proportional to the length. So rest of the quantities are the constants here. So that means here if I divide these two, VAP1 divided by VAP2 will be is equal to E1 by E2. So I can write it is constant multiplied by some L. K is a constant. So K L1 divided by K L2 is equal to E1 by E2. So from here I can write L1 by L2 will be is equal to E1 by E2. So this is the simple like comparison of two EMFs. L1 is the something like this, the length, balancing length. So this length not necessarily 100 minus L. We don't require even it as of any length. So how you will determine the internal resistance? So for that purpose, here you do one thing, you connect some other battery, other resistance. Let's say I call it the S resistance. In the secondary circuit, we are connecting another shunt. So with the help of this smaller circuit, I can determine. So then what will be the potential difference now? The potential difference across that AP will be is equal to E minus IR. So here the current flows now. Here the current is going now. This current I call as IS. E1 or otherwise simply E minus IS into R. So potential difference across AP will be E minus IS can be written as EMF divided by total resistance, that is S plus R into R. So when I take the LCM, what will be the cancel here? ER will be cancel. ES divided by S plus R. So now with the help of these equations, with the help of these equations, I can find the internal resistance of a cell. Let us see how I can determine. So the first equation what I got, VAP1 will be is equal to EMF multiplied by the, that is K multiplied by the EMF, and this K multiplied by L1 will be is equal to E. This is the first equation. The second, when I connect it to the shunt, then potential difference VAP2 will be is equal to, that's what I calculated here. I got it is ES divided by S plus R. ES divided by S plus R. So now it is K multiplied by L2. K is the constant. Just now I explained to X plus R. So now you do one thing, divide both the equations. So KL1 divided by KL2 will be is equal to E divided by ES into S plus R. See here, E cancels, no use. So KK also cancels, L1 plus L2 by S plus R by S. So from here L1 by L2 will be is equal to 1 plus R by S. So from here L1 by L2 minus 1 is equal to R by S. From here I required R. R is equal to S into L1 by L2 minus 1. So L1 is the balancing length without any secondary resistance S. L2 is the balancing length when I place the secondary resistance in the potentiometer circuit. Okay. So these all things, you know, they are not the new things I said already. I hope it is clear. So I just explained all the concepts clearly. Important things, current density, that important relations, then followed by resistance. That is, the resistance means it is indirectly the Ohm's law. Then based on the resistance, what type of problems will be asked. Then variation of resistivity with temperature, how it varies with the temperature. So then afterwards, important thing, that is the power and heat. Then cell charging and discharging, series combination and parallel combination. What is the maximum power transfer theorem? Then importantly, Kirchhoff's current law with junction rule, Kirchhoff's loop rule, that is voltage law. Then galvanometer, what is the sensitivity of a galvanometer, how it will be used to measure the current, how it will be used to measure the potential differences, the conversion of galvanometer into ammeter. So ammeter is always connected in series with the circuit. Then voltmeter, which is always connected in the parallel combination. Then another important instrument is the Wheatstone bridge. We mostly use in the balanced Wheatstone bridge. And similar to that, there is a meter bridge. Then that is the conditions we wrote here. Then another important thing finally is the potentiometer will be used to compare the EMF of two batteries and internal resistances. So this is the formula for measuring the or comparing the EMFs, and this is the formula for measuring the internal resistance. Okay, I hope everything is clear. Thank you for watching my entire lecture. Please subscribe my channel. Don't forget, like and share.